So yeah, we probably won't finish all of this. Actually, I guarantee you we won't finish all of this today. But this is the topic-related rates. We'll probably spend at least 2 classes, maybe 2 and a bit, see how we feel about it in double block. But what I want to give you an idea of what we're actually doing here. And the first thing we'll take a look at is this idea of an oil slick with the radius expanding. So I'll show you a picture, but I don't want to say too much because it sounds complicated. I mean, it's hard to say some things in math without sounding ridiculously complicated, especially in calculus. So let's just take a look at some of the people who've had some time to go and make visuals for these problems. So here on the left-hand side when it loads is an oil slick. Right now it's not moving. On the right-hand side is the area that the oil slick is starting to grow to. So for example, when I start this, you'll see that the dot there on the left side grows, and you'll see the graph start to move as well. So it's growing, and on the right side, this is what's happening to the area. Okay. So would anybody say, or could they explain possibly why, if the radius is moving at a constant speed, that the area looks like it's getting quadratic, like an x squared? Any idea why they might affect each other that way? Yeah.
Does r get squared?
You're right. Be more specific, though, for everybody.
That formula, pi r squared.
Yeah, area is pi r squared. So area increases. R squared means it's going to be squared when we see it in the area. So that's what's happening, and that's what we're going to look at today, is how the change in one variable affects the change in the other variable. Okay? So let's try a problem and see what exactly this would look like. Now, there's, like in your textbook, there's about 6 steps in related rates problems, and they're just tremendous. They're horrible. There's really only 2 that you have to know. Whatever extra steps you do in the middle to help you figure out those 2, that's really, you just need to know these first 2. So this is what we're going to think about every time we come across one of these questions. The first thing is, it really sounds ridiculous, but it's worth repeating, is what am I looking for? If you can't answer this, we won't be able to continue this problem. It takes a little practice to figure out what they're talking about, but I'll show you in a second. It'll make a bit more sense why we have to think about that. And then number 2 is, how are the variables related in the problem? And usually we're looking for a formula. Okay, so again, usually this is a formula that we're talking about. So we're going to start around pretty simple for the level of difficulty, and then we're going to kind of escalate a little bit. And as we get further up the chain, you're going to feel like, holy smokes, we need another day, and you get it. You get another day on this. Okay, but for the first one, let's try and answer these questions here. The first thing says, how fast is the area of the oil slick increasing? So this is actually the question I'm being asked, is about the area increasing. Out all that there, that's what I want to know. So in calculus, the way we're going to write this down is I'm actually looking for the change in the area with respect to time. So we just talked about implicit differentiation. The reason we just did that is because it leads nicely into these related rates problems. So how fast is the oil slick's area increasing? I'm looking for the change in area with respect to time. If you haven't already been doing so, it will make a lot more sense to you if instead of reading this as dA dt, that you actually say in your head the change in area with respect to time. Okay? Now, how are the variables in the problem related? So what variables do I have in here? Should have downloaded the Jeopardy music. Connor, yeah?
You have the area and the radius.
Area and radius, yeah. There's 2 variables I'm working with here. So how are they related? How can I come up with an area and a radius somehow in relation? Well, that one is going to be area equals 2 pi, sorry, not in this world, maybe in another one, but area equals pi r squared. Okay. So the reason I want to find a connection, like I just did here, is now I'm going to take the derivative in this formula. So if I take a derivative, it's going to be the change in area, and I'm going to do it with respect to time. Things are moving here. This radius is growing. Things are changing. So I'm taking it with respect to time. And on the other side, so remember, r squared becomes 2r times the derivative of r with respect to time. So this is how the area is rate of change relates to the radius's rate of change. So the question says, when the radius is 25 meters, how fast is the area increasing? So radius is 25. That means right there, I'm going to be able to put that in for the radius. It tells me here the oil slick's radius is expanding at a rate of 2 meters per minute. So that's going to go into here. So that means the change in area at that particular moment, or instant rather, would look like this, and that's 100 pi. Now my units, if you pay attention to what's inside the question, all of my units are in meters per minute. So when I'm dealing with the area, it's going to be in meters squared per minute. Now, some people were like, oh, isn't that acceleration, you know, like meters squared per second? And you got to remember that this is a rate of change in the area. This piece right here, if I go like this, the meters squared part is area, and it's changing at a unit of time in minutes. That's why there's a meters squared per minute. Right? It's kind of weird to talk about area changing, but that's the units that we're dealing with, meters squared per minute. Okay? Now the second part says, if we start with a radius of 0 when time is 0, how fast is the area increasing after 3 minutes? So this question is almost identical, but you have to think a little bit harder to figure out the pieces of the puzzle. Okay? This is still the relationship that we have, and the one that we're looking for right now, which is, let me just get my pen here. Nope, not going to do it. 1 second. Do it the old-fashioned way. There. Okay. So this is still the same relationship, but instead of knowing what the value is for the radius, it's telling me the time it's interested in. Can anybody figure out from 3 minutes? How could you figure out how big is the radius at 3 minutes? Yes? You were right. Say it. 6. How did you do that?
3 times 2.
Yeah, 3 times 2. We know it's going at 2 meters per minute, and 3 minutes have elapsed. That means the radius is now, at 3 minutes, the radius equals 6. So this time, the change in area will be 2 pi times 6 times 2, which is 24 pi. Well, it doesn't really look like a good 24 now, does it? 24 pi. Okay, and again, those units would be in meters squared per minute. Okay, this one I'm not going to jump onto the internet for, but again, I picked these first set of examples because they all have applets that you can go and look at home if you're kind of confused as to the relationships. I'll show you a couple others, but let's just talk about the first 2 things again. The most important questions for a related rate is, what am I looking for, and how are the variables related? So can we answer the first question? What am I looking for if they ask me to find the rate the snowball is shrinking? Any ideas? Okay, I promise I won't pick on you, but hands up if you think you know what you're looking for here as a related rate. What are you looking for? You know it? Maybe? Okay, some of us are shaky. Okay, well, something is shrinking. How would we sort of measure it shrinking? So like think about if you blow up a balloon and the air is shrinking out of the balloon. Right? How would you measure that? Say it louder. Yeah, in this case we actually know it says the radius is shrinking at 2 centimeters per minute, so you're correct, but we already have that information. But how else could we describe the way this balloon would be, or in this case a snowball, is shrinking? Yeah, volume, right? Because if we were to describe it by its volume, that would tell us, the size change at any instant. Okay, so what we're looking for here is the change in volume with respect to time. And we have to figure out, okay, we've already said some of the variables. So Gary, what was the one you said? Radius. And Alex? Volume. So think about a snowball. Is there anything else in this problem that we'd incorporate? It's a sphere. It's a really bad one that I'm trying to hold up for you, right? It's a ball. Can you think anything else that we might need to work with? Yeah, I know. It feels that way when you start related rates. I'll put you, there are no others that we need to work with, right? Because a sphere is what we're going to be dealing with here. So how do we relate volume to radius with a sphere? Does anybody know the formula for a volume of a sphere? Ah, resourceful. Nobody knew it in first block. Oh. That's correct. Okay, so the volume is 4/3 pi r cubed. So remember that there is no formula sheet when we come down to your AP exam, but sometimes they're nice enough to put those formulas into the question, but sometimes they're not. So we'll get practice because we'll be using more of these geometric formulas throughout the year. But anyways, maybe if it was like, I don't know, the area of something strange. What's a strange figure? A cone, right? A cone's not that common. That one might show up, whereas the area for a sphere is a little bit more, or volume for a sphere is a little more common. You might be expected to know it. Okay, so we've got our first two questions, the most important ones answered. What am I looking for? Change in volume with respect to time. How is it related to the variables in the problem? It's through the volume formula here. So I'm going to see, can you figure out how to answer the rest of this question now that we've answered those first two? So I'm going to give you a couple minutes to see how you do. Okay, so let's see how we did. This is the change in volume with respect to time. So if I move the 3 to the front, I'm going to end up with 4 pi r squared, and then the change of r with respect to time. We're always doing this implicitly because it's with respect to time. So you should always have as many of these fraction-looking things as you have variables. So now, what I'm looking for, the formula is all set up. I just have to be able to substitute. So it says the radius is 20 centimeters, and the radius is shrinking 2 centimeters per minute. If it's shrinking at 2 centimeters per minute, tell me something smart about that. Calculus smart. No one's feeling calculus smart? You have to be careful about this. Yeah, that's calculus smart right there. Nicely done. It has to be negative because it's shrinking. The rate of change is getting smaller. Or sorry, it's got to be negative because the radius is shrinking. So if we do this, 4 pi and then 20 squared times negative 2, I believe that means we're going to get negative 3,200. Is that right?
Yeah. Well, I don't know.
408. Is that okay? Now, why should that be negative? Tell me why the change in volume should be negative. It's melting. Yeah, the snowball's melting. If we didn't have the negative here, it would say the snowball's growing, right? So it's not tumbling down the hill in the Arctic somewhere. It's melting somewhere in the sun. Okay, the second question says, what if we want to know the rate at time 10? So 10 minutes. How do we figure out this relationship? Our formula is based on the radius. Okay, I'm looking for that, the change in volume. That I've been given, but in this question now I haven't been told what the radius is, I've been told what time. Can everybody figure out how to do that?
10 times 2. So 20, yeah.
So let's hear it, DJ. You sound like you've been working something out.
Oh, because it's 2 centimeters per minute, so times 10, so it'd be 20.
20. So what about 20? You're correct so far?
20 is the rate of change.
20's...
I mean the radius. 20 is radius.
So close. So close.
I don't even know how to say
So,
it. DR over
Yeah.
DT.
It's how much has been melted, how much we've lost. So if we've lost 20 centimeters and we started at 70, that means the radius now equals 5. Sorry, 50. That time equal 10. The radius is 70 minus
Yeah, it made so much sense.
2 times 10,
So, if
which will be 50. So then I would have 4 pi times 50 squared times -2, which of course is going to be even bigger, so I'll leave it there. I don't particularly feel like doing that in my head. So, questions about this example so far? So I'm going to let you try the next one right from the beginning. So tell me again what my favorite, well, maybe not my favorite, what are the most important questions you need to ask yourself here?
moist.
What am I looking for? If you can't tell me what you're looking for, you won't be able to find it. What's the second thing? How are they related? Okay, so here's the next question. See if you can do it by yourself.
I'm so excited. Let's do this.
Okay, so I'm going to show you the first couple of questions. We'll talk about 1 and 2, and then we'll see how we did for finding the actual related rates there. Okay, so
Take the derivative of that.
so here's the applet so that you can kind of compare what your intuition tells you versus what's happening.
16 squared is still just a number.
Now, so here's the height of the ladder. Here's the distance from the wall. Now this time, as I pull the ladder away from the wall, I want you to watch the top of the ladder. I'll do my best to pull it at a constant speed, but anyway. Is it bad luck to fall when a ladder
No,
falls?
wait, that's walking under.
Under it, yes, okay. So think about it this way. How much has the ladder moved now? Look at the top of the ladder.
Not a lot.
No.
Not very much. Okay, how about if I keep going further?
More.
Okay, how about now? Whoa, too far. So what do you think is happening to the top of the ladder if I move at a constant rate? I mean, this is my best I can do with a constant rate here, is if I go like this. What's happening to the top? How could you describe, let's see, I try it from here. How could you describe the top there?
It accelerates.
It's going faster, right? It's constant from the bottom, but the top is going faster towards the ground. Okay? Now, the second question says, if x is increasing, will dh by dt be positive or negative?
Negative.
So x is the distance that the ladder is away from the wall. So why don't we put this in here as a picture? So here's the wall, here's the ladder, here's x, here's h, the ladder's 16. So as x goes this way, it gets further away from the wall. Would you expect the height to be positive or negative? Go for it, Gary. Tell us why. You're correct. Yeah, the ladder's going down. This height is getting smaller, so this would have to be negative. The change is getting is negative because the height is shrinking. Okay. Now, this is the first part where we'll actually talk about doing the math for it. Suppose the bottom of the ladder is 5 feet away from the wall, and it slides away at a constant rate of 3 feet per second. Find the velocity of the top of the ladder at time 1. So what am I looking for? Sorry? Exactly. So what I'm looking for is in calculus lingo would be dh dt, the change in height with respect to time. Okay. That's what I want. And according to my picture here, this is why pictures are nice when you do related rates. You can kind of look at it and see what numbers and variables are involved. So how can we relate those numbers or the number with h and x? Any ideas? I know some of you when I walked around had the correct relationship here. Do you have it? I don't know, you looked excited like you wanted to say something.
Square root of 16 squared minus x squared.
I think you're talking about the right thing. It just sounds complicated. Can you help me out? Just tell me what you're using. Yeah, that's right. So with Pythagorean theorem, right, we're doing implicit differentiation. We don't need to do square roots. We can simply say 16 squared equals h squared plus x squared. Okay, we can leave it this way, because now when I take the derivative, I'm going to get 0 equals 2h dh dt plus 2x dx dt. How do you get which? Remember, we're always going implicitly because we're doing this with respect to time. That's why these extra pieces here pop out. Okay, those have to be there because it's with respect to time. Now, I'm going to do a little rearranging. This is what I was looking for here, dh dt. So it will be negative 2x dx dt equals 2h dh dt. And that means these 2's will cancel out, and I'll end up with dh dt is equal to negative x over h dx dt. So, what pieces do we know the information of? We need 3 pieces in order to answer this question. We need an x, we need an h, and we need a change in x with respect to time. So which of those 3 pieces do we already know? We definitely know x because it says right here, the ladder is 5 feet from the wall. What else do we know? We will know h, but it's not given to us. Okay. Do we know dx dt, or do we have to go looking for it? What is it?
3 feet a second.
Yeah, 3 feet per second. Should it be positive or negative? Positive, yeah, because it's getting bigger. This value for x is growing. The rate of change has to be positive. So what I can put down here will be negative 5, and there will be, sorry, what do we say, 3? Yeah. And we have to figure out h. All right, so height, or what will the height be at this? Anybody know? Danny, did you figure it out?
I said 7.
That's correct. How'd you do it? You don't have to give me all the algebra. Just tell me how did you know you could figure it out?
Time is 1 second, and the rate is 3 feet per second. So the changing x is plus 3.
Okay.
But put 3 to 5, because the divisor is 8, and it's the Pythagorean theorem.
Okay, so
Oh, chill.
it made sense to me. It's 5 feet, and then we're moving away from the wall at 3 feet per second. So that means it's gone from 5. 1 second later, it will be 8. So the x value here should actually be an 8. And it's gone from, it started here, and it just moved 3 more feet. So it was at 5, it's now at 8. Okay? The value for h, well, here's something that might help. Right, we can just do some trigonometry like Pythagoras theorem to find that value for h. So this would say h is the square root of 256 minus it's x squared, which is 8 squared. So that's 256 take away 64, which is square root 192. So that's the missing piece that we were still looking for. Okay? So what I'd like you to do is try to rework this. Suppose the top of the ladder is sliding down now, not the bottom being pulled out. Okay? This time find dx dt when the height equals to 12. Okay, so very, very similar. You should be able to reuse everything from about this step here. Something from about there on you should be able to reuse. Okay, so I'm going to clear some of my work just so that I can catch up with you. if we were to rework this question,
Oh, okay.
Sing.
so this time I'm looking for dx dt. So I'm going to rearrange on this side, and I'm going to have dx by dt. That's going to be h over x, be a negative, times dh by dt. So again, now it's just a matter, now that I have the relationship, it's a matter of figuring out what values go in here. So the ladder is sliding down at a rate of 4 feet per second. How do I use that? That's some information. How do I use it? It is dh dt. Be careful. It's negative because the ladder is falling. H is shrinking, so the rate of change has to be negative in order to decrease. Okay, so dh dt here, this is going to be a negative 4. And, well, I know here it says h equals 12, so it'll be negative 12. And I have to figure out what's the value for x at this point. So I'll do it the same way we did in the last one. This time it's 12, so 12 squared. 256, take away 144, so it will be 112. Okay, so I guess we could call that 48 over root 112. And if you think about it, this should make sense why we had to include a negative too, because the result here becomes a positive because x is increasing, so the rate of change should be positive. Okay, so let's try another here while we're on a bit of a roll. I have to apologize to those of you at the back for a minute. I have to shrink this just to fit it. So, water pours into a conical tank that is radius 4 and height 10 at a constant rate of 10 cubic feet per minute. So you just think about it as a tap's been turned on and the tap is still flowing, just steady rate of water coming in. Okay, so we're gonna, pictures are always good for us. They help us, keep all track of the information. Let's start there. Okay, let's, well, no, I need blue for the water. Let's use black for the... So this is what a conical tank looks like, a cone. And it tells me that the radius is 4, and the height is 10. And we should have like a... I don't know how to draw a tap there. Let me just, we'll make water. No, that's gray. 1 second. There we go. Isn't that pretty? Yeah, it was never my strong suit.
It does look like enough.
So, there's the information so far that we've been given. I haven't included this yet. What would the best calculus way of describing 10 cubic feet per minute be? How could I write this into my picture? Let's think about this. What is 10 cubic feet? Volume. So how can we write this information in a calculus kind of way? Yeah, so the change in volume with respect to time is 10 cubic feet per minute. How fast is the water rising when it's 5 feet high? So let's put the water level at 5 feet high. Okay. So here are the pieces that I have so far. There's a radius, there's a height, and there's some volume here. Can anybody figure out a way to connect all these pieces together? Look in the back of your book. Yeah. So, you want to help us out, DJ? Oh, you've already got it there? Okay, so what's, tell us about it?
Pi r squared h over 3.
Pi r squared h over 3. So the reason I'm going to walk you through this one is we could go ahead and do this with the information that's been given, and we could go in autopilot. But there's going to be product rule here, right? There's a product rule. And if you notice, I've only been told the water level is 5 feet high. I don't have the radius. I would have to find the radius. That's possible. But what I can do here to avoid all that extra stuff, sometimes it's necessary, this time it's just going to be nice, is use similar figures, okay? So what I'm going to say here is this triangle, I'll draw them for you. So let's say this triangle is the big triangle. Okay. And there's a similar triangle right there for the small one. So the two similar figures have to have the same proportions. So that means 4 is to 10 as r is to h. So I could write this down like that. And that way, it says to me 5 feet high. I'd like to keep the height in this problem, but I don't have any information about the radius. Okay? So what I'm going to do is replace it. So this is going to say 4 over 10 h is the radius. I guess that would be 2 out of 5 h. Because if you think a few steps ahead and you start doing this derivative, somewhere in there, there's going to be a dr dt. Have you been given that information? We don't have it. So we're missing the radius. We're missing the rate of change in the radius. We're also missing the rate of change in the height. There's too many variables. We won't be able to solve this problem if we jump right into it. So sometimes you may have to replace a variable in order to take, cut them down from 2 variables to just 1. And that's what we're doing here. So if we substitute that back in, this will become pi, and the radius now is the same thing as 2 over 5h squared. And the way I'm going to want to work with this, if I square 2 out of 5, what do I get? 2 out of 5 squared is, we've forgotten over Christmas break possibly? Yeah? Yay, yeah, it's 4 over 25. Okay, so it's 4 over 25 pi, but we've got this pesky 3 here still. So the friendliest way, I guess, that we would want to deal with this will be 4 pi over 75 h cubed. Okay. So now I'll be able to solve this because I got rid of the r. It's almost a given. I don't think I've ever seen one of these tank questions where you haven't had to do this replacement by similar figures. Okay, so just a heads up for you when you do them. If I take the derivative, the change in volume with respect to time is going to be, okay, if I multiply by 3, this 75 turns into a 25. Is that, everybody? Yeah. Okay, so that's going to be 4 pi over 25 h squared dh dt. So we want to know how fast the water level is rising. So what I have to do is I have to solve for this dh dt. Right now it's not set up for me. So dh dt, I'm going to take this h squared and this 4 pi and move it to the bottom. When it comes across the equal sign. And I'm going to take that 25 and put it up. So it'll be over here. And it still leaves me with a dv dt. So I can substitute all the information in now. In my particular spot, the height height is 5, and the volume is increasing at a rate of 10 cubic feet per minute. So this would tell me how fast the height is rising. Okay, so I'm going to draw a picture for you on this one. You probably feel like we're kind of going up difficulty level. We are. And as I told you, we're going to spend at least 2 blocks on this. So, you know, it'll sink in a little more with a bit of practice and a bit more work at it tomorrow. Today, in this one, we're still kind of raising the difficulty a bit. But I'm going to draw you the picture. I'll do that part of it, and then I'll see if you can work the rest of it out. In this question, you live in a house. And 1 mile from your house, there's an intersection on a highway. And a car is driving down the highway. And we're interested at 3 miles past the house. So let's just say the car is here. So put some rims on this thing. Well, apparently it's going in the wrong. Anyways, yeah. And I wasn't around in kindergarten when we had car drawing day, but I'm not very good at it. So it says here, the car is 3 miles past the house. So let's say this distance is 3 miles, and the house is 1 mile. Here's the distance between the house and the car. What we'd want to know is, if this car is moving at a rate of 60 miles per hour, then how fast is the distance, this here, how fast is this distance changing as the car goes by? Okay, it's still moving in that direction. Okay, so I'm going to let you talk about, there's some things I haven't labeled yet in this picture. I'm going to let you try and work on the rest of the picture and see if you can come up with a related rate here. Okay, so here's the things that we're talking about so far. We've had a few conversations as I was walking around. This distance between the house and the road, does that ever change?
No.
It's constant. The road and the house don't move, so we can leave it as a 1. Okay? This line, though, the distance between the car and the house, it does change. So we should give it a name. Let's call it D for distance. Okay? What about this distance? The only one we haven't talked about is this distance here. Constant or a variable? The car is moving, so yes, it is a variable. It's moving horizontal, so I'm going to give it a variable of x. Right? That, like we're moving along the x-axis kind of thing. So now, what am I looking for? In calculus language, please.
The change in distance with respect to time.
Exactly. So this is what I'm looking for. I have to figure out how these pieces are related in order to do that. Okay. I know there's a Simpsons episode. I don't think it's on YouTube, otherwise I'd try to find it for you, where they're doing, it's when Homer goes, I think it's when Homer goes back to the nuclear college. Has anybody seen that one? Anyways, and they're talking about something to do with derivatives, and it's RDRR is the one, and it's like the funniest, right? RDRR? Is that? Anyways, never mind. Catherine gets it. Okay. So how are these pieces related? Can anybody say it in a sentence? Or tell me how could you relate them? Starts with a yes. Say it. Say it. Yeah, go for it. Pythagoras again. So this is 1 squared plus x squared equals d squared.
I knew it was
Okay.
too easy.
So if I take derivatives on this with respect to time, 2x dx dt equals 2d dt. Yeah, there's a lot of d's in there. Okay, perhaps I should have chosen a better letter, but those 2's would disappear. And what I'm looking for is if I solve for dd, that's going to be x over d times dx dt.
Okay, now we can do it. Yes.
Phew, okay. So I know that x at that particular instance is 3 miles. I can figure out that d would have to be the square root of 1 squared plus 3 squared. So that'll be root 10. So this is going to be 3 over root 10. And the car is moving at 60 miles per hour. Okay. Good news. Last one. Hey. Okay. Time flies when you're having fun. That's right. Okay, so this question, this is another. I mean, I guess it's semi-famous. It's probably close to the cone. I think this one, it's very elegant, meaning it has a very nice, simple solution, but how you find the solution takes some creativity. So I'm going to just show you guys how this one works. I remember this because it was on my calculus final when I was in university. So I don't know if the professors still like it, but it is a popular one. So let me show you, we should start with a picture, right? We got a 15-foot lamppost, and do they make, is that really, maybe they are that tall. And let's see here. There. Give it some realistic graphics. And there is a skateboarder, so
You're trying so hard.
okay, and everybody knows that skateboarders have long blonde hair, right? And they say things like, "What's up, bro? Dude."
Cool story, bro.
Cool story, bro.
Okay, and to think about this is asking the rate at which the shadow is increasing in length. So it's asking about the shadow that's being cast. So in this picture, we want to figure out how can we draw this shadow. So, I mean, we all know, hopefully we all know how shadows work, but when the light is being cast from this bulb, at some point the body blocks the light and that creates the shadow. So if I think about it this way, here's the beam of light as it gets to the top of that skateboarder, and this is about where the tip of his shadow would be, right? So here's the ground. I mean, it's not a very good road to skateboard on, but there you go. That's what I'll have there. His shadow would be somewhere up there. Okay, so maybe, I don't know, what the heck, I'll give it a whirl. It would be something like this, I would think then. It's going to be bigger than him because, I don't know, how's that look? Is that good?
That's good enough.
No? Okay, but this is the way the shadow works. I'm going to get rid of my my masterpiece there for a minute, just so it's a little cleaner in the picture. And now what we're going to do is start labeling things in this picture. We got a good picture, well, a semi-good picture, I guess. We know that the lamppost is 15 feet high. We know the skateboarder is 6 feet tall with the skateboard. And we know that that skateboarder is moving at a rate of 3 feet per second. So since they're moving horizontally, why don't we call that the x distance? Let's say this is dx dt. So that means, according to my picture, this is x. And the good thing about that is the shadow starts right after that. This would be the shadow here. So if my masterpiece was still there, that would be a shadow. Does anybody think they could come up with a clever way of relating all this stuff together? It's awesome if you can, because usually it takes people, they need to see it first. Yeah, that's right. It's similar figures. So you can see there's there's two triangles. You want this side of the triangle, and there's this side of the triangle here. They both have the same piece for the top, and along the bottom there. So what I can say is 6 is to 15 as the small piece here, s is to the whole thing x plus s. So 6 is to 15 as s is to x plus s. Now what I mean by there's a, if you can get there, that's fantastic, but now look at how simple this derivative is going to get. You can take the derivative right there if you really, enjoy the quotient rule, but why don't we do this instead? This relationship should still be true. Right? And this relationship should still be true also. So that means if I take the derivative, that's what I end up with. So if I want to know the rate of change in the skateboarder's shadow, maybe I'll move this up a little bit, then the change in the shadow will be, let's see here, 6/9 times the speed of the skateboarder. And that's also 2/3. So why don't we say 2/3, and they're going 3, was it meters or feet per second? I think feet. Okay. So this shadow is increasing at 2 feet per second. So you should all go home and try that with someone who's 6 feet tall on a skateboard just to verify it.